Swayam Prabha. Digital India. Educated India.
Yeah, in the last few classes, we have been looking at the handling characteristics of a vehicle. Now, in that process, we developed, of course, the understeer gradient, and we also brought in a very simple technique called the Mimuro rhombus in order to understand the vehicle behavior. These are, simple techniques, but lot more things happen in the actual vehicle. In other words, the understeer gradients, one of the definition for understeer gradient is given by WF by C alpha F minus WR by C alpha R. Remember, I think I wrote that as K2 or something like that. Okay, this was multiplied by AY, if I remember right. This is what we had defined. We defined two ways in which you can do it, or in other words, we defined with two terms the understeer gradient. The other term, the other understeer gradient is m into BC alpha R minus AC alpha F divided by L squared into C alpha R C alpha F. That's the other term. So these are very simple definitions which came out by looking at the tires interaction with the vehicle and the road. But then the tire interaction should be brought out in a much more detailed fashion, and that is what we are going to see in this class. And we are going to take whatever we are going to learn today to the next topic of subjective and objective evaluation of a vehicle. Okay. What do we mean by expanding this topic? It's very clear that this is affected by the weights that act on the front and the rear. Okay. There are other things that happen in the car which are going to affect this WF and WR, as well as the assumptions that we have made regarding the linear behavior of the tire. Remember, what are the assumptions that we had made in our bicycle model in order to obtain the definition for this understeer gradient? One is that we neglected the roll. Number two is that we assumed a linear behavior of the tire, right? And we neglected all other aspects of suspension and steering. Handling is all about how the vehicle behaves when I give an input to the steering. By now, we would have realized that. Now, the input to the steering is, of course, under your control, and that is what is going to also give you a feedback about the vehicle. So we have to understand in a much broader perspective these things. Okay, let us now look at first from a physics point of view, what happens when you do not have a tire which is linear. In other words, if I remove this assumption of linearity of a tire, let us see what happens. Okay. Before we go into the equations, let's see that. I'm going to follow Gillespie, for this lecture, but then we will take over and then look at other things from next class. And please pay attention to this, because this forms the basis for evaluating a car. In other words, it will be exciting to know how you are going to evaluate a car. If you're going to buy a car and you want to drive a car, what all you should do in order to understand the behavior of the car is going to be the next lecture, and for that, this will form the basis, right? Okay. Now, let us look at the actual diagram for the C alpha F. In other words, how actually the force developed, okay, in terms of the slip angle. Note that we had already said that Fz, the normal load, is going to play a role in the development of Fy. In other words, the stiffness, what we call a stiffness, depends upon the normal load that is acting. Okay. Now, why are we harping on this? Basically because when you say, for example, when you want to take a turn, all of us know that the vehicle is going to roll. Okay. Especially initially when it's going straight, both the wheels, left and the right wheels, within small tolerance, would say that both of them have the same reactions. Okay. So when there is a roll of the vehicle, then these reactions, what we call as WF and WR, are going to change, and the left wheel is going to have a different reaction, and the right wheel is going to have a different reaction depending upon one is going to be higher and lower depending upon whether you take a turn to the right or left and so on. Right? So what is important is to understand what happens due to load transfer. This is one type of load transfer. The other type of load transfer happens when you take a turn and start accelerating or decelerating. Okay? Again, all of you know that there is a load transfer from the front and the rear. So the load transfer to the front and rear, whether it is due to braking or traction, is again going to have an effect on these things, and is going to have an effect on understeer and oversteer gradients. So load transfer is going to have an effect, and so this is the first thing. So we have to understand how C alpha F varies. Let us say that, let me plot it like this. Let's say that this is the vertical load. I'm going to plot the graph of, remember that we plotted alpha versus Fy. I'm going to plot this graph slightly differently. I'm going to say that Fy, and I'm going to plot it for different alphas. Okay? Let me call that as alpha 1, alpha 2, alpha 3. Okay? So for different alphas. Right. Now, of course, alpha 2 is greater than alpha 1 and alpha 3 is greater than alpha 2 and so on. Right? Now, let us say that I have, say, 4,000 Newton that's acting in a tire. Okay? And that produces an Fy. That's the Fy which produces. And that's good enough for me to say, is what good enough for me to equilibrate the centripetal accelerations. Okay? Right. Now, when there is a roll, why there is a roll? We will see it in a minute. When there is a roll, in other words, when the left and the right, or inner and the outer, or however you want to call it, okay, when the loads get redistributed, look at what happens. Okay, for the same alpha 1, which is the slip angle, okay, when the load comes down, say for example it comes down to 2000, okay, the load or the stress, the force that is produced comes down. Okay, and for the other tire, which is going to increase to 6,000, this is going to increase. Okay. Now, this gives rise actually the total Fy, which is going to be less than what is produced before. In other words, because of the non-linearity of the curve, note this carefully, because of the non-linearity of the curve, when there is a change in load, the alpha that is produced is not good enough to equilibrate the centripetal acceleration. It's going to fall short. Okay? So there has to be a larger alpha. There is going to be a larger alpha. Okay? Please note this is left and right. This is a tire, which is left and right. So front there is a left and right, rear there is a left and right. And remember that in our model we have C alpha F and C alpha r to depict the stiffness of the front and the rear together in toto, right? So what will happen now, because of this, it is not good enough. The Fy is not good enough to equilibrate centripetal acceleration. So this alpha has to shift up. The alpha that is produced is to shift up, right? So that if this were the equilibrium, say let's say that it is 3800 or something like that, if this has to be the equilibrium force, okay, now I'm falling short, maybe I will get say 3400, okay, that difference of 400 has to be generated, okay, so I have to work at a higher alpha, and that is such that, okay, I'll just exaggerate that here. So this is the one which was initially was like this, okay, and I had fallen short. So I have to now increase my alpha such that I come back to that 3800. Okay. So in other words, the role, the redistribution of the forces result in a change in the operating alpha. Right? Now look at that closely. When there is a change in alpha, alpha f and alpha r, that is going to produce a change in the understeer gradient. Okay? Because after all, that is alpha f minus alpha. Remember, our delta is equal to alpha f minus alpha r and plus L by r and so on. So alpha f and alpha r are going to have an effect on the understeer gradient. So the very first thing is that due to this role, there is a change in the operation of alphas, and hence I have to have an additional term to my understeer gradient. Right? So what are the things that I have to do now? First of all, I have to find out what is this change. What is this change? Right? Between the left and the right, or outer and inner. Let's call it as outer and inner. Left and right is not the correct one. Outer and inner. Right? What is the change? Once I work out this change, then I have to introduce, the first thing is, so the derivation which I have to put now is what is the change in the normal That's the first thing I have to find out. What is the change in the normal load? Okay. So the next is next thing is that remove the linear assumption for the tire and introduce a nonlinear relationship. Let's call this as a, say, quadratic relationship. Let's say quadratic with respect to Fz. Okay, quadratic with respect to Fz. Please note, when I say linear, the linear relationship in the sense that we had only one C alpha F. That's what I mean by a linear relationship. In the sense that there's only one C alpha F. It was independent of Fz. Okay, it's independent of Fz. But actually, it is not independent of Fz. So we are, in other words, Fy is a function of, say, A into Fz. So that, that's the only thing that we said. Now we are going to say that it's a quadratic with respect to Fz. We will introduce that in a minute. So note what we mean by that linearity. The linearity is with respect to Fz. Okay. So once I do this, then calculate the new alpha. That's what we're going to do. Right? let's look at a very simple diagram. We will make this, we'll make a few comments to make it a bit complex. And let's say that I have a solid axle. Just for illustration, we will see how it can be looked at for independent suspension. Okay, let's say that okay, that's the sprung mass of the vehicle. Okay, and that is the what we call as the roll center. We'll define this as roll center. I mean, we'll see what it is in a minute. Maybe you know that already. Roll center. Let us say that there are now Fy and Fz forces that are acting on the tire. So where will be the Fy forces that will be acting? Fy will be in the towards the right or the left? Right. Okay. So this we will call as Fy outer and Fy inner. Right? And of course there will be a normal load that will be acting, which we would call as Fz outer and Fz inner. Yeah. So this is turning like this. So actually like this to the right, and so the roll is to the left. That's why I call this as outer and this is inner. I don't want to call it as left and right, okay, because it can be the other way. Right. Now, the concept of roll center, I'm sure you had heard about this, that roll centers form a roll axis. I know that you had heard about this term roll axis, and about which actually the sprung mass rolls. Another way of looking at roll center is the center about which you can split, in very simple mundane terms, you can split the sprung mass from the unsprung mass. So for example, if you want to draw a free body diagram of this especially for these forces, okay, then I can say that is where I would take the reaction for the Fy. In other words, okay, the reaction for Fy, okay, for this would be about that point. So that would be the Fy. Okay. Of course, Fy is equal to Fy naught or O outer plus inner. Right. So my job is to find out how does this vary. Okay. In order to do that, I have to look at what is called as roll stiffness. I have to look at the roll stiffness. Okay. As the name indicates, it has everything to do with roll. So it relates the moment that acts to the angle of roll phi. Right? Okay. Now we will talk more about this roll center. Right now we will say that there is a front roll center, rear roll center, and they join, and what results in the roll axis. Okay, and about which this roll takes place. Right. So let's say that this is S, and let's say that this is T, the track. Whatever derivation I'm going to put here for the rigid axle can be extended to a independent axle, independent suspension. For example, that's what you do for a car, okay, independent suspension, by assuming that all these stiffnesses are dumped at the wheel position, right? So it's very, very close. So it's somewhere here. You can assume that it is a track which is S. Clear? Okay. Now, let's say that that angle, okay, to which it rolls is phi. And that difference in the height is delta z, and hence phi is equal to delta z divided by S. Clear? Okay. Now help me to determine what is the roll stiffness. Note that delta z is equal to F by Ks. Okay? Right? How do you go about this? How do you think we can go about this? Simple, yeah?
Delta z is P times S.
Yeah, so F into S, which is creating the moment, okay, is equal to the roll stiffness K phi into phi. The moment that is created by this force is actually equal to the K phi into phi, right? From which you can write down half into Ks into S squared is equal to K phi into, okay, that's substituting for phi from this expression, okay, and then calculating the delta z by the difference, okay, I can write down that K phi is equal to half into Ks into S squared. Right. So this is what we call as the roll stiffness. If I now, so this is the relationship between the spring stiffness and the roll stiffness. Okay. What I essentially did was to find out what are the forces, two forces, that causes a moment, and that moment is what is given in the left hand side. Okay, force into moment, distance, and the right hand side is the one which equilibrates it through K phi into phi, which is K phi is the roll stiffness, okay, right, with force per degree or radians multiplied by the degree. Okay. Now, as I told you, the first step is to find out what is the change in the normal load. Okay, in order to do that, let me use this diagram. Let me take moment, okay, let me take moment of all the forces that are acting about the center. Okay, about the center. Now, the springs take the normal load, and as I said, Fy, okay, when I cut it, this is Fy is where the reaction for this is taken. Right. Now, how do I write this? F is at naught into T by 2, okay, about this, and that's the clockwise direction, right? Then minus F is at inner into T by 2. This is in the anti-clockwise direction, right? Then minus Fy, right, into H, right? H is the height, and that is equal to, that is the total moment that is created, that's in the anti-clockwise direction, that is equal to k phi into phi. The moment that is created, what causes the roll? That's what we are doing. So the moment, the total moment that's created is what causes the roll. Okay? This is just for one suspension. We had said what is the connection between the two, and so we now have k phi into phi. Rearranging these terms, f z is at naught outer and minus f is at inner. Bring that fy in the other, to the other side. So it becomes 2 fy into h divided by t. T is a track plus k phi into phi, okay, into 2 divided by t. Let me call that, I have to put the equation numbers properly, and let's say that I'll call this as equation 1 and that as equation 2. Yes?
Can you explain whether we taking reaction force into
At this point, because I want to find out the difference between f is at outer and f is at inner. So that is that's what it is. Remember that f is at outer plus f is at inner is equal to wf. So two equations. Okay? So my job is to find out what is f is at outer and f is at inner. Right? That's why I'm taking the moment about this. So that makes my job easier because my expressions are neat. Right? If you want to take it about any other point, as long as you get f z outer minus f z inner, it's fine. Right?
is roll center same as center of mass?
No, center of gravity locations are different. So the roll center is different from center of gravity. Okay? It is, do you understand? It is the instantaneous center about which this rolls. Okay? That is not the CG location. In fact, the roll center, I'm going to do that now. Okay? The roll axis is at a distance from the center of gravity, and that's going to cause a moment, okay? A moment about the roll axis and so on, and which we'll go to derive now. Okay? So, in other words, if you look at the side of the vehicle, right? So the roll axis, say for example, this is the center of gravity location, then there is a front roll center or rear, let's call that as rear and that is front. Okay? There is a front roll center, right? And the line joining these two is what is called as the roll axis. Okay? So it is an imaginary axis which runs about which this whole body rolls. Okay? So that is the roll axis. So a moment which is created because of the distance, say for example, the center of gravity location is away from it. Okay? So the center of gravity at which, see here is the point. So let me draw the same, let me cut that and show it, or let me assume that to be a three-dimensional view. I mean, this is just an imaginary line I've drawn. Let us say that that is the center of gravity location. That's the center of gravity location. Okay? And this is the roll axis. Let's say that that is the height h, right? And the roll happens about this. Okay, the roll happens about that. So the center of gravity location now rolls or moves, okay, by an angle phi. Okay, and for the whole body, you know that that's where the weight W acts. and we know that that's how, say, Fy acts. Right? So the moment about the roll axis then is given by the moment created by that W as well as Fy. Clear? Okay. Any other question? Right? Okay. Write down the moment now. Let's see. Write down the moment. Let's call this as H1. Okay. The moment is now given by, there are two things, H1 into, that's phi. So W into H1, let me call that as moment. W into H1 into sine phi, okay, that's the sine phi, plus Fy is mv squared by r, v squared by r. As our practice, we will call that as, we'll write it like that, so that that becomes Ay. Okay, into cos phi. And that the roll axis is inclined at an angle psi, or epsilon rather, small angle. So that also, the cos of this is actually the factor which has an m phi. So that multiplied by, look at the geometry, you would notice that there are two angles. So that would be cos epsilon. Now I'm not going to make it so complex. I'm going to assume that phi and epsilon are small. Okay, so that becomes 1. This becomes 1, and that becomes phi. Yes?
Does the vehicle have just one single roll axis?
Yeah. Two roll centers, front roll center and the rear roll center. Front roll center and rear roll center are characteristics of suspension. There's a method of calculating, geometric method of calculating the roll centers that you would have studied in the vehicle systems.
Center of mass would lie either to the left or the right of the roll axis.
Yeah, but now we are saying that it lies right here, okay, right at the top because of the symmetry positions, okay. We assume that it is symmetric, okay. So roll axis would lie right at the bottom, okay, right. We are not, it won't be unsymmetric. So we are looking at the symmetry. There's no reason why this has to be unsymmetric, right. So simplify this. So that is equal to what is that? Take out the W, H1. So W, H1, sin phi becomes phi. So V squared by RG E plus phi. That's the moment caused by this phi. And this is also equal to, what is that equal to? This is also equal to K phi front. What's K phi front? Okay, plus K phi rear. Okay, that is the roll stiffness multiplied by phi. Yes. V squared by RG. Okay.
Phi H1.
Where did I leave H1?
There. V square by RG H1, and then there will be again H1 with W.
उससे ऊपर कहीं
और-
पे गलती की है इसने।
Of
Look at that carefully and tell me. Obviously, here I left out H1. Okay. And so this H1 will be there. Okay, obviously that will be a h1 into cos phi, right? So h1 into cos phi. Right. So let me simplify this and look at what is phi. Remember, why are we doing this? Coming back to this graph, I want to find out what is the change in alpha. So let me call that, let me give that equation numbers correctly. Let me call that as 4, that equation number 2. Let's call that as equation number 3. Let me call that as equation number 4, because when I resubstitute it back, that would be fine. Okay. Now let me rearrange those terms here in this so that I would get phi. So my whole idea is to get phi, right? So WH1, let me rearrange that. I'll say WH1 into V squared by RG is equal to K phi front plus K phi rear minus WH1 into phi is equal to, so that phi is equal to WH1 V squared by RG divided by K phi F plus K phi R minus WH1. All right? Okay. Now, the automobile engineers define what is called as roll rate. Define what is called as roll rate, which is d phi by d ay. Note that carefully. It is not phi dot. Though I call this as roll rate, it is d phi by day. What is that? Simple. That is ay, and so differentiating the first term. So this would be WH1 divided by K phi F plus K phi R minus WH1. That makes life easier when you want to define, and it's about 5-6 degrees usually per G. It's degree per G. So in other words, that tells you if you know the roll rate, and if you're taking a turn and you say that I'm subjecting my vehicle to 0.3 G, then just multiply by roll rate, you would know how much is the roll. Right? Clear? Fine. Now, let us find out, let's go back to equation number 2. Right? I've written that correctly. Now, let's go back to equation number 2. Right? Okay. Let me write down that equation to the front and the rear. Okay? This is generally we have written. Okay? Up to this, I've written down generally, then the whole vehicle. So let me go back to the equation number 2 and write it for the front and then write it for the rear. Okay, I'm going to write down the final, that expression, and that's quite simple. It's not K phi F into phi of F, or K phi F into phi is equal to delta F is at front divided by 2 into TF minus WF HF into V squared RG, and K phi R into phi is equal to delta F is at F by 2 into TR minus WR HR into V squared by RG. Okay? What's that I have done? I have just defined now delta, what is now delta f is it? Look at that term there. What is delta f is it? Not what is delta f is it. So this term, what is this term? That's the last term. Okay, that's the last term. What is this term? That is the fy into h by t. That's this one. Okay, so fy I have substituted in terms of wf into v squared rg. So delta f z by 2 is what I call as f z naught minus or o minus f z I. Right? Okay. This is implicit assumption here in this step. The rest of it is only jugglery. There is an implicit assumption. The assumption is that the whole body is stiff and that there is only one roll. Though we said that this is applicable for front and rear, actually the whole body rolls as 1 phi. Okay? So that is what is this expression. Now once I know what is k phi f, which is actually the property of the suspension, and once I know these factors, I can easily find out what is delta zf, sorry, delta zr, okay, and delta zf and delta zr. It's straightforward from these two expressions, and let me call that as 4 and this expression as say 5 and that as 6 and that as 7. Right? Okay. So that's what I wanted. What is delta f is at front? The difference between the outer and the inner. And delta f is at rear, which is the difference between the outer and the inner in the rear. Okay? Once I know that, I am now going to use that in order to determine how my alpha f and alpha r varies. Any questions? Right? Clear? Okay. Now remember that we had this expression in the front as C alpha f into alpha f, and at the rear as C alpha r into alpha r. Okay? Let us now assume that C alpha f has a quadratic expression, okay, which I would write as A f z f minus B f z squared, okay, into, so that this would become into alpha f. Right. Now, note that this, if it is for single tire, C alpha f is written for single tire. For our bicycle model, I have to multiply this by 2. So I will get 2a f z squared minus 2b, sorry, f z f minus 2b into f z f squared. Right. Now, fy, say fy front or rear, is the sum of f z outer plus f z inner.
Get that expression for C alpha f.
What is it? I assume. This is what I assume. Okay. Now, is it correct? Okay, it's an approximation. Actually, we don't use in practice this expression. Okay, actually, we can find out all these factors, say for example, by assuming the tire to be a Paseka model, right? And then we can get this correct redistribution, okay, by this. Now, note that f z outer is equal to normal f z which is WF. So I would call that as normal FZ plus delta FZ. Delta FZ is that by 2, okay, and FZ outer, sorry, inner is equal to FZ minus delta FZ. Okay. Now, substituting that, sorry, FZ outer, no, this is FZ, not F. Now, substituting this expression, which I would call as, this is called as 8, and that we would call as 9, this whole expression. Substituting 9 into 8, okay, 9 into 8, and then expanding this expression, expand that expression, I'll write the final form. I can write down FYF, okay, in a much broader expression, taking into account the non-linearity with respect to FZ. Do that, this is a very straightforward exercise. So now Fy, substitute it and then simplify it. So you will get 2a Fz minus 2b Fz squared minus 2b delta Fz squared into alpha. Remember, what is delta Fz? Okay, so that it is delta Fz naught minus delta Fzi divided by 2. Okay, so that's the what we had there, half of it. So Fy is now given by this expression. Okay, so in other words, if there is no load transfer, this would have been the C alpha F. I told you that. Because of the load transfer, that 2 into C alpha F, the 2 into this, that is affected, and you have an additional term. So let me call that as 10. Right. So I will write this as Fy front. This is Fy, general Fy. Okay. Outer and inner can be in the front as well as in the rear. Right. So Fyf can be written as, since I said that is the C alpha F, C alpha F minus 2b delta Fz front squared into alpha F. Fyr is equal to C alpha R minus 2b delta Fz rear squared into alpha R. And what is this? And this is equal to Wf into V squared by Rg, and that's the Fyf, and that's equal to Wr into V squared by Rg. Remember, what is my delta? Go back and have a look at that. What is delta? L by R plus alpha F minus alpha R, from which my whole definitions, everything came out. Right? And remember, alpha F was written by Wf by C alpha F and so on. Right? So that is what will give me also my definition for K. I'm going to substitute, see, let me call that as 11, and that's 12. Substitute 11 for alpha from 11 to 12. Okay? And then we will get an expression for, a new expression for delta. So what is that essentially we did? Just recapitulate, we will expand that in the next class. Essentially what did we do? We realized that the load transfer is going to change alphas, okay, and the load transfer is due to roll. and that the roll is controlled by what is called as roll stiffness. And the roll stiffness comes from the suspension stiffness, right? Okay, these are the things. So now using that and using simple equilibrium, okay, due to forces that are acting in the body, we find out what is phi, right? And then from this, we assuming that the tire has a nonlinear relationship with respect to Fz, okay, we find out, okay, the changes in alpha f because of introduction of both this nonlinearity as well as the roll. Okay, that's what we did. Clear? So that gives rise to an expression for alpha f, which is Fy divided by this, Fy divided by that expression, okay, and alpha r is equal to Fyr divided by that expression. Okay, so I'm going to substitute that and then write down delta is equal to L by R plus Fyf divided by C alpha f minus 2b into delta f z squared plus Fyr divided by C alpha r minus 2b delta f z r squared. Yes.
When we say delta, it will be different from left and right.
Oh, sorry, minus. Exactly. So in this model, in other words, we are not considering it as 4 tires. Okay, this is a simplified model. In practice, in actuality, okay, this won't be the case. What you're saying is absolutely right. So alpha f front outer would be different from alpha f front inner and so on. Okay, now we are getting a gross effect here. The advantage is that we can look at it very easily and tell what would be the effect of roll. The disadvantage is that it has its limitation of having only one tire compressed, a bulk quantity, and one tire at the rear. Right? So this is a very simplified model, the bicycle model, but helps us to understand, okay, what happens when there's a roll transfer. So in actual, if you want to really design a car, then you would take up to commercial, say, softwares that are available like CarSim or Adams or one of them, okay, in order to understand actually how does this happen. Now the whole idea here is to only illustrate, okay, in simple terms what happens. Okay, and we're going to use this in order to look at how to evaluate a car. Right? Load transfer has an effect on understeer or oversteer, period. One statement. How? In a simplified form, this equation is going to tell us. That's it. Clear? Okay. We will see the rest of it in the next class.